Very good morning to everyone. So today we are going to see the part of design of concrete structural system of CLE 5002 by myself, Professor Senthil Panyan. Just we'll have a small introduction. What about the limit state? What is the case? We'll see. So before going to a little small introduction, what is mean by the structural design? The structural design is an art and science of creation of economy, elegance, a safe, serviceable, and a durable structure. So what about it? The basic, the knowledge of such a thing, it's required knowledge of practical aspects. So practical aspects is more important, such with the relevant codes, bylaws, and ample of experience and the judgments are more important. So before going over that structural design, the base is the analysis. There are two methods of analysis: manual computation method and computer method. Right now we are busy. In manual, the slope deflection method, strain energy method, the most famous moment distribution method, and the Kanish method. In computerized method, matrix methods, that is stiffness matrix method, flexible matrix methods have been used. Next, finite element method and finite difference methods. So these methods have been used in the computerized. Now many softwares have been used only based upon these methods only. So what is the major design process? The design process is going to be the first a preliminary design has to be done. See in the preliminary design, what is the thing we generally we used to do is we'll put the beam and column profile. What is mean the beam and column profile? What will be the position of your beam and what will be the position of your column? What will be the position of a case? And we'll have some amount of temporary the sizes of the beam and column. And next we will go for analysis, structure analysis. And next it will give us some of the response such as a bending moment and shear forces. And based upon bending moment and shear forces and what the material we are going to use, the material parameters comes over to it. If it is satisfactory, then we will go for the drawing. And if it is not satisfactory, then we have to change the cases. What are the cases we are going to change? Maybe as changing in your size of your beam, size of your column, or preliminary design as can be changes or analysis slightly can be modified. Eh, So this is how the design process comes over to the picture. So next, what is the case? The major thing of the construction is the structure is going to be the economy is more important. Next, the safety of the structure is more important, and the cost. So the combination of the economy, the cost, and the safety, they is called as an optimum point. So the optimum design, I guess, so how much amount of the amount of material we are going to use. So what will be the cost of the building, and what will be the safety of the structure. So this all are going to come in the optimum design. So what are the types of design methods available in this case? There is the working stress methods. Okay, working stress methods that is used to call as a WS method. That is based upon the factor on only materials, and the stresses are within the allowable limits. Within the allowable limits. In ultimate load method, that is we generally used to the factor of loads, design load, that is equal to the load factor into the expected load. So maximum what is the expected load. And the last one is the limit statement, the LS of the partial factor on both material and as well as the load. So two cases here. So in this one, working stress and limit state are being there in right now. The ultimate load method are in very rare cases. Then in 99% the limit state methods have been used. In wherever the limit state method cannot be used, the code recommends to use the working stress method. The ultimate load methods are not being used much unless it has been specified. So let me say about what is meant by the limit state. What is the limit state method is nothing but the combination concept of the ultimate load method and the working stress method. That is, the partial factor of safety on materials and partial safety of the loads has been used. So uncertainties of the both materials and load can be considered realistically. So it can be used a realistic one, and different limit states have been considered. So that is a collapse, serviceability, and the durability. So let me see about what will be the stress strain curve for this all cases. So let me say this stress strain curve. The stress, the one working stress limit, the stresses will be allowed only within the limit. It's not go beyond. So the strain will also within the limit. But limit state, it goes up to the maximum of 0.002 mm, 2 strain, and for ultimate it goes up to the maximum. And this is going to be the experimental where it's going to be fall. So what are the types of limit states available over here? There are three types of limit states. What are the cases? Limit state of collapse. What are the limit state of collapse? What are the cases of fracture, compression, shear, and torsion? Where in limit state of serviceability, deflection, and cracking. Where limit state of durability, time dependent deteriorations, creep, fatigue, and deficiency are all comes in the durability cases. So what are the partial safety factor? The partial safety factor for the loads and as well as the material. So here partial safety factor, the code recommends IS 456 recommends per dead load and live load approximately 1.5 where wind load is 1. So wind load structure which is more than 10 meter are to be considered as said in the IS 875 part 3. So here it comes to limit state of collapse and the limit state of the serviceability. Where live load over here, partial safety 1 and 1 in serviceability, where it collapse 1.5. So similarly the leg is well for earthquakes, the earthquake load can be substituted for the wind load conditions. So it says. So what are the partial safety for the material strength? So according to the code IS 456, there may be a large amount of faults due to the workmanship, construction, and the supervision. So the sum of the material partial safety factor has to be given over the case. For the limit state of collapse, the value of the partial factory factor gamma m can be taken as for concrete is 1.5 and for steel is 1.15. So when assessing the deflection, material properties such as modulus of elasticity should be taken as those associated with the characteristic strength of the materials. Let me have the some amount of reflection. So when a beam is subjected to have a bending, that is a resist for the transverse loading. When it's having for transverse loading, it is used to have the fixed bending moment, where it is going the moment and the shear are going to be taken place in a beam, where the top member is going to be act as a compression and bottom is going to be as a tension, where the couple is going to be act over here. So this is how the action of a beam, action of a beam. So let me see about some amount of assumption made in the limit state. So let me say in for limit state of collapse inflection. Whenever a plane section remains plane during the process of bending. So even after bending it, we have been assumed that it will be straight, the section. And the compression strain in concrete at outermost compression fiber is 0.035 and the tensile strength in the concrete is totally ignored. So these are the assumptions is said. And the strain in the tension reinforcement is should not be less than 0.87 Fi. The 0.87 Fi is nothing but the 1 divided by 1.15 gives us a 0.87 by elasticity of seal plus the allowable strain of the case 0.02. This is assumption is instant to ensure the ductile failure, that is in the tensile reinforcement has to undergo a certain degree of inelastic deformation for the concrete fails in the compression. So this is the idealist curve for concrete. So what is the idealist curve for a concrete here? This shows the case. What is the characteristic strength of your concrete? This is the actual strength of your character FCK. And after applying the material safety factor, we are giving that is 1.5. That is 1 divided by 1.5 gives us a 0.67 the case. After that, based upon the load factor over here, that is 0.67 by the gamma m is going to come upon. That's much amount of the case we are allowing. That much amount of the stresses only we are allowing into the structure. This is for the mild steel. So mild steel is the one. So Fy is the ultimate. This is the yield load of the rebar, where the ultimate how much amount of the stress we are allowing is 0.875, where it's nothing but the Fi divided by 1.15, where elasticity of steel is 2 into a power 5 Newton per mm square. The same thing for the deformed bar stress strain curve. So now we are coming to the stress block diagram. This is the more important when you are going for the design of your beam. So here let me consider this a beam over here, and the breadth of the beam, and the depth of the beam, that is called as effective depth, and overall depth is going to be the depth of the beam. And here the rebars are going to come upon, and this is the neutral axis going to be case. So as far as our assumption, we never allow any stresses, that is tensile stresses to the concrete. We will allow only the tensile stresses only to the rebar. So first we will see about how the strain diagram is. As far as we know, the assumption is that extreme one, okay, the extreme one of the concrete case is going to have the strain of 0.035, where we are allowing maximum to that 0.02 the strain, whereas in the strain at the steel is 0.875 years per point, where the case we are going to allowable strain. So the actual stress diagram is good. The maximum stress is going to be acted. That is the maximum compressive force is going to be acted over at this point, where we are going to 0.002, the strain point, and where the maximum strain stresses, tensile stress is going to be acted only at the rebar, where we call it as the TU. That is to use the tensile forces. Yes, the compressive forces must be equal to the tensile force, compressive force, and where the ideal stress curve is we are going to follow. The follow make a stress. So what is the case? We are going to have the case. So are we the point 935? How much amount of the case we are going to have at the 0.446? That's FCK. That is nothing but that 0.67 FCK divided by the 1.5 gives about the 0.446 FCK. Okay, so that resistance has been over here, and here we'll have about the maximum based upon the idealist one, the XU max. What is the XU max? The depth of your neutral axis, depth of your neutral axis. Using this, we can identify what will be the distance of the 0.43 XU, and minus over here the 0.43 and 0.57 the XU max can be identified over here. So we know what will be the XU. Using that one, you can find out the XU, that is depth of the neutral axis is equal to D minus XU max over here. The stress strain diagram can be case. So now let me identify what will be the XU max value. That will be the XU max is going to be come upon over here the 0.40 XU max. So first for that we must know about what was the area of the rectangular case, area of the stress block. We must know about the stress block because the stress is going to be here only act at the case, and here in the in the concrete. So the area of the rectangle. So here the case. So rectangle is here and the parabola is here. So first we will be calculating A, B, C, D, the area of the rectangle point, A, B, O, the area of the parabola. So what will be the case? 0.446 into 0.43 FCK into XU. So it gives about 0.191 FCK into XU max. And next the two-third of the 0.5, that is one-third of the 0.57 XU max into 0.167. So it gives about 0.169 FC max in XU. So it gives about 0.36 FCK in XU. So how much amount of the force is going to be acted over here is the area, that's the amount of stresses is 0.36 FCK into XU max. This was the area of your stress block diagram. So from this we can calculate what is the central point. What will be the central point over here? What will be the point of the neutral axis? So XU, the center of the axis, we have already calculated the 0.19 FCK XU into 0.214, 0.214 over here from 0.214 from the XU max plus 0.169 FCK. So from there we can calculate, that is 0.214 is going to come over here. And next from here we are going to calculate the 0.65, 0.243 plus here. So 0.653 XU max divided by 0.36 FCK is going to come about 0.42 into XU max. So we'll get about the 0.42. So repeating over here, X is equal to base of the stress block diagram, the 0.19 into of the center of this one, and from here to here and the center of this point gives divided by the area of the stress block gives about 0.4 to xu max. So now we know about the 0.4 to xu. So depth of the neutral axis is equal to d minus 0.4 to into xu max. This is how we are calculating. So how to calculate the maximum depth of your neutral axis? So maximum depth of the neutral axis can be from the stress strain diagram. From the strain diagram, we can calculate what will be the maximum depth. Nothing but xu max divided by d minus xu max. This is what the case. So we know already the extreme cases we used to have this maximum strain of 0.0035, and we know the extreme stage at the rebar, that is 0.87 Fy ES plus 0.002. Using this, we can calculate what will be the xu by d. This is the way. So this is majorly depend upon your what the type of rebar we are using. If the rebar is been case, then maximum of your the neutral axis within 0.31. If it is 419, is 0.47. If you are using 500, it is going to be 0.456. Okay. The singly reinforced section. So now we will be seeing how the single reinforced section we are going to calculate. The rebars. So always you will be having the structure should be stable. So further what will be the case? Compression should be always equal to the tension. So we know the how much amount of the tensile forces is equal. So this is Fy into S. That's allowable yield stress into how many number of area of the rebars divided by your factor of safety is 1.15 divided by 1.15 gives about 0.8. So we calculate how much amount of the compressive forces comes, that is 0.36 FCK into xu max into what will be the breadth of your section, gives you what is the compressive forces going on. So you know now your compressive forces, and this compressive forces must be equal to your tensile forces. So this is how we have made it. So now I know it. So now how much amount of the percentage of the reinforcement as percentage of AST into divided by BD into 100 gives. So we calculated the AST is equal to 0.36 FCK B into XU max divided by 0.8 something. So you can from this you can calculate how much amount of the percentage of reinforcement is limited to your structure. So let me see the limiting moment resistance or the reinforcement index of the single reinforced section. If the yield strength of the bar is 250, 415, 500, then the moment limitation is 0.149, 0.138 and 0.13. The limitation of the reinforcement is 21.97 or 19.82 or 18.87. This all have been given in your SP16 code book. So let me have the sum of the thing. In single reinforced section, there have been three cases have been I think. That is under reinforced section, over reinforced section, and balanced section. The three sections in each case is going to be there. So generally, the people will be designed only for the under reinforced section and balanced section. Let me see about the under reinforced section. In the under reinforcement, the percentage of reinforcement should be always less than the percentage of limit. The steel of yield before the concrete presses the compressor. The steel yield first, then the concrete gets cursed. And the required steel reinforcement should be less than the maximum. That is, the depth of neutral axis is less than the maximum neutral axis. The failure characteristics by the substantial deflection and excessive cracking and giving ample of. So some amount of cracking will be come upon a excessive cracking, and the deflection will be shown before the structure gets failed. So you will have some amount of time to repair the structures. So this is the idealist one. So this is the under reinforced section. You can see that the neutral axis come above the top. So near the in concrete, it has a lesser number of tensile forces. All maximum tensile forces will be taken by only the steel, and the only limit compression only it's taken by the case. Where in balance, the compression is equal to the tension it has been designed. A over reinforced section we can see over the case. The maximum of cases comes over by the over reinforced section, the rebars, the maximum compression. So that you can see here the how the stress block diagram over here. You can see the very clearly that case. So that's the reason the people will be going with the balance section or under reinforced section. So this is the flow chart how the analysis used to be done. So find out the percentage of the percentage limitation, that is a reinforcement limitation. The first, if it is less than the percentage limit, then it is going to be anti reinforcement. If it is equal to balance, if it is over. If it is over the case, then we will be take XU is equal to XU limit, since the over reinforcement is not permitted, and we'll do the design based upon the case and we'll do. If it is the percent limit balance section, then XU must be the XU limit, And after that we will go directly to the formula over here and we'll be doing the design based for the most up on the moment we will do the design. If it is under reinforced section, then we have to identify how much amount of the tensile forces are going to tension forces are going to come in your structure. And next we must know the we have to assume the what will be the depth of the neutral axis. And next we have to identify the what will be the maximum strain in the concrete. If it less than 0.01, this display parabolic. If it greater than the case, the parabolic and the straight. And next for the case we have to see about the stress block, how much about the compressive forces over here. And here the find the depth of the parabolic and the straight portion, what is the depth. And next once again here also we have to identify what is the stress block comes over, whether it's the compression is less than tension or equal to or greater than. Based upon that we will calculate the what will be the lever arm stresses. And once the lever arm stresses have been calculated, you can calculate the reinforcements. So this is how the analysis used to be done. So first you have to identify your compressive force, what is the forces, and next you have to identify the what is the load factor, next material factor, and next we have to go for the compression is equal to tension, and you have to make your design. That is, you have to check for the steel and next for the concrete, and that's how you have to do the design. That's it. Thank you.